Section 2.5, continuity. We are going to demonstrate an understanding of and discuss the continuity of functions. So intuitively, we think of something as continuous if it has no breaks or gaps. For example, I-95 is a continuous road from South Miami to Maine. You can drive up the entire east coast of Florida. You can drive up the entire east coast of the United States without ever changing roads. So a function, then, is continuous if it has no breaks or gaps. We will use this intuitive idea of continuity to define what it means for a function to be continuous at a point and also on an interval. So the next four pictures give us some examples of functions that are not continuous, and we're going to use these to see if we can come up with rules for determining discontinuities in a function in terms of limits. So this first function here, we can see it's discontinuous at this point C because there's a hole in the graph at C. Okay, so that's a gap. And in terms of limits, we can see that if we approach that point C from the left, or if we approach that point C from the right, we are approaching the same limiting value. So the limit exists. However, the function is not defined. Okay? So that is one thing here, then, that we're going to have that destroys continuity, a function not being defined at a point. All right, so in the second case here, we actually have that the function is not defined, but also we have that the limit as x approaches C does not exist. Okay, because it increases or decreases without bound depending on what side of the C that we're coming from. All right, so here's another example. Now here, f of C is defined. However, we can see that there's a discontinuity, and in terms of limits, we can see if I approach from the left, I'm approaching this value here. But if I approach from the right, I'm approaching this value here. Okay, so actually the limit as x approaches C of this function does not exist. Okay, so even though the function is defined at C, the limit doesn't exist, and so we have a break in the function. And then finally here we have the function is defined. Okay, and if we approach from the left or the right, we are approaching the same value, so the limit does exist. Okay, but the problem here is that these two things are not the same, right? So we still have the gap and a discontinuity. So basically these four examples give us things that destroy continuity. Okay, so the function is not defined at a point C, so we saw that in examples A and B. The limit does not exist at a point C, we saw that in examples B and C. And then the function is defined and the limit exists, but the limit is not equal to the function value at C, and that's what we saw happen at D. So basically these are the three things that will destroy continuity in terms of limits in the function. All right, so in the picture below, the domain is from 0 to 4 inclusive, and we want to determine at which points on its domain is it discontinuous and why. At the endpoints, we always have to consider only one-sided limits. All right, so at first we're going to look at the point at the endpoints at 0. Okay, so as x approaches 0 from the right, because we can't come from the left, it's outside of the domain of the function, As x approaches 0 from the right, the function values are approaching 1. So the limit as x approaches 0 of f of x exists, and it actually also equals the value of the function. And this means this function is continuous at x equals 0. All right? So it's going to actually have a discontinuity here at x equal 1. And so it's going to be discontinuous. And that is because the limit as x approaches 1 of the function does not exist. Okay? And the reason it does not exist is if we approach from the left, we're approaching 1 from the left, we're getting 0. But if we're approaching 1 from the right, so from this direction, we're getting 1. Okay? And so since the left and the right-hand limits are not the same, this limit does not exist, and that is one of the things that destroys continuity. Okay? So we have that it's discontinuous here at x equals 1. So that was our first point of discontinuity. Okay? Here it's discontinuous at x equal 2, but in this case we have that the limit as x approaches 2 of f of x does exist, because if we approach from the left or the right, we're always approaching 1. Okay? But the problem is that it's not equal to f of 2, because f of 2 here is defined to be 2. Okay? So the limit exists, the function is defined, but those two things are not equal. So we have a discontinuity at x equals 2. Okay, so there's our second discontinuity. All right, we can see here that the limit exists and it equals the value of the function. So that would mean it's actually continuous. So it's going to be continuous at x equal 3, because the limit as x approaches 3 of f of x is equal to f of 3. Okay, so it's actually equal to the value of the function. Okay, and then the last point in question would be at the other endpoint here. And remember, at this endpoint, we only have to consider the left-hand limit now, because it's at the endpoint of our domain. So if we look at the limit as x approaches 4 from the left of f of x, this exists, and it's actually equal to 1. But that is not equal to f of 4, because f of 4 is down here at approximately 1/2. Okay, so again, the limit exists, the function is defined. However, those two things are not equal, and so we have a discontinuity at x equals 4. Okay, so basically, this is how you would show that there are discontinuities in a graph, by showing either the limit doesn't exist, or if the limit exists, it does not equal the value of the function, or the function is not defined at that point. So those are the three things we look for when we're looking for discontinuities. Okay. So the formal definition of continuity says that if C is a real number, that is either an interior point or an endpoint of an interval in the domain of f, then the function is continuous at C if the limit as x approaches C of f of x is equal to f of C. So notice that in this definition, where there is the assumption that this limit actually exists, and it has to equal the function evaluated at C. So the function is called right continuous at C, or continuous from the right, if we're on an endpoint of the interval and we're looking at the right-hand limit. So this, for example, was right continuous at x equals 0. Okay. And then left continuous would be similar when we're looking at the left-hand limit. All right. So the definition above defines continuity at a point C, and we define a continuous function as a function that is continuous at every point in its domain. Okay, so if it's continuous at every point in its domain, then we have a continuous function. Okay, and so here's just that picture of continuity from the right, continuity from the left, and two-sided continuity. All right, so that leads us to this test for continuity. I've already said it before, but we'll say it again. A function f of x is continuous at a point x equals c if and only if it meets the following three conditions. F of c has to exist, the limit as x approaches c has to exist, and these two things have to equal each other. All right, so here's an example. It says, discuss the continuity of this function. All right, so to discuss the continuity, the first thing we need to know is the domain of the function. Okay, and since we're taking a square root, that means that the 4 minus x squared has to be greater than or equal to 0. Okay, and that's only going to happen when x is between -2 and 2. Right? Because if I have anything bigger than 2, then I'm subtracting something bigger than 4 when I square it, and also anything less than -2, the same thing, so it would end up being negative. So x is going to have to be between -2 and 2, so that is the domain of our function. So now we want to know, is it actually continuous on its entire domain? And what we have to do is, first of all, we're going to let c be any point in the interior of this interval from -2 to 2. Okay? Then the limit as x approaches that point C of the square root of 4 minus x squared is going to equal, according to our limit properties, the square root of the limit as x approaches C of 4 minus x squared. And since this is a polynomial function, we know that this is actually equal to the function evaluated at c. So this is going to equal the square root of 4 minus c squared, which is equal to f of c. Okay? And so basically what we showed here is that the limit exists, and it actually equals the value of the function for any point on the interval from -2 to 2, not including the endpoints. And the reason we don't include the endpoints is because at the endpoints we have to look at left and right-hand continuity. So at -2, we have to look at right-hand continuity. So we're going to look at the limit as x approaches -2 from the right of the square root of 4 minus x squared. And again, just using our properties of limits, this equals the square root of the limit as x approaches -2 from the right of 4 minus x squared. Okay, which is going to equal the square root of 4 minus 4, or 0. Okay, and so again, we have that the limit exists, and it equals the value of the function. Okay, so this is actually equal to f of -2. All right, so since the limit exists and it equals the value of the function, it's continuous at -2. And similarly, we can show as we approach +2 from the left, this is going to equal the square root of the limit as x approaches positive 2 from the left of 4 minus x squared. And that is, again, going to be the square root of 0. And it equals the value of the function at 2. All right? So basically what we've shown is that for any point in the interval, the open interval from negative 2 to 2, the limit is equal to the value of the function. And then we went to the endpoints of the interval, and we showed that the right-hand limit is equal to the value of the function at that endpoint, and the left-hand limit is equal to the value of the function at the other endpoint. And therefore, what this means is, since the rule for continuity means the limit has to exist and it has to equal the value of the function, we have that this is actually continuous on its entire domain, which is from negative 2 to 2 inclusive. Okay, so it's continuous on its domain. So we want to discuss the continuity. So 1 minus x is a polynomial function. So when x is strictly less than 0, this is going to be continuous, because for a polynomial function, we know that the limit as x approaches c of, I'll call it p of x for a polynomial, is always equal to p of c. And so we're going to have it continuous for x less than 0, so anywhere on this piece of the graph. And if we're between 0 and 1, okay, not inclusive, we know that e to the x is a continuous function. So the limit as x approaches c for any point on this interval of e to the x is simply going to be e to the c, okay? And therefore, we have its continuous on the open interval from 0 to 1. And then finally, we can say the limit as x approaches c of the x squared plus 2 is equal to c squared plus 2, which is the evaluation of the function, because this is a polynomial function, right? And so we also have that it's continuous for x greater than 1, okay? So basically, each individual piece is continuous. So the only thing that we have to question is when it stops following one piece of the graph and starts following the next piece, okay? And that would be at 0 and also again at 1. So we want to now check to see, do we have continuity at x equals 0? Okay, and do we have continuity at x equals 1? Okay, so to check that, we know that we're going to look at the limit as x approaches 0 from the left, and that needs to equal the limit as x approaches 0 from the right, and that actually has to also equal f of 0. Okay, so that's basically the definition of continuity right there. All right, so when we're approaching from the left, we're on this piece of the graph, okay? And so the limit as x approaches 0 from the left means we're looking at this piece of the graph, which is simply going to be 1. Okay? The limit as x approaches 0 from the right means we're on this piece of the graph, and that limit is going to be e to the 0. Which is also equal to 1. Okay? So basically we have that the limit as x approaches 0 of f of x is equal to 1, and this equals f of 0, because f of 0 is e to the 0, which is also equal to 1. All right, so we have that it's actually continuous at x equals 0. Okay? And now we have to also check at x equals 1. So we have to do the same thing. We have to look at the limit as x approaches 1 from the left and see if it equals the limit as x approaches 1 from the right, and see if that equals f of 1. Okay? So the limit as x approaches 1 from the left of f of x. Okay, so when we're approaching from the left, so that would be numbers smaller than 1, we're on this piece of the graph. So that's going to be e to the x, which is going to be e. If we look at the limit as x approaches 1 from the right, when we're approaching from numbers bigger than 1, we're on this piece of the graph. It's actually x squared plus 2, right? Okay. And as x approaches 1, this actually approaches 3. So since the left hand and the right hand limits are not equal, that means the limit as x approaches 1 of f of x does not exist. And that means we have a discontinuity at x equals 1. Okay? So that means basically this function is continuous everywhere except at x equal 1. And therefore we would say it's continuous on the interval from negative infinity to 1, union 1 to infinity. So basically we have everything less than 1, everything greater than 1, and we are simply excluding x equal to 1. All right, so properties of continuous functions. Basically, if two functions are continuous, so is their sum, so is their difference, so is any constant multiple times a continuous function is continuous. The product of two continuous functions is continuous. The quotient of two continuous functions is continuous, provided that g of c is not equal to 0. If I raise a continuous function to a power, it's continuous. And if I take the nth root of a continuous function, it's continuous, as long as that nth root exists. Okay? So functions that we know are continuous everywhere are going to be polynomials. So any polynomial function is continuous, since we know that the limit as x approaches c of a polynomial function is just p of c. And similarly, we know for a rational function, it's the quotient of two polynomial functions, so it will be continuous as long as the denominator is not equal to 0. And lastly, if I know that one function is continuous, then its inverse function is also going to be continuous. And then this last theorem here basically says if I have the composite function of two continuous functions, then that composite function will also be continuous. So we can actually use the properties here to show that these functions are continuous. So for example, this is actually a composite function with, I'll call it f of x equals this, and g of x is equal to the square root of x. Okay? So, because then if we take g composed with f of x, we basically get this function here. All right, so this function is continuous on its entire domain because it's a polynomial. So it's actually continuous from negative infinity to infinity. Okay. This function is continuous from 0 to infinity. Okay, and we can show that because, again, if we take the limit of the square root, it's the square root of the limit. And so those limits are going to equal the value of the function. Okay, so we have the composite of two continuous functions. So it should be continuous as long as the radicand, remember, because we're taking the square root here, so as long as this is greater than or equal to 0, because that was the restriction on continuity for the square root function, this function should be continuous. Okay? But basically, we can say that this function is going to be continuous on its entire domain. So this function is going to be continuous and its domain is going to be the values of x that make this inequality true, which we would have to use like the quadratic formula to find those out, okay? But basically, we just want to show that it's a continuous function. And so, since it's the composite of two continuous functions, then it should be continuous on its entire domain, okay? And similarly here, we have x to the 2/3 is basically the cubed root of x squared. Okay, so for a similar reason, we're think of this as a composite of the cubed root of x and x squared. And so we have a continuous polynomial function, and the square root or the cubed root of that is going to be continuous. And here we also have a continuous polynomial function, okay, in the denominator. And as long as the denominator is not equal to 0, this one is also going to be continuous on its domain. Okay? Again, because the numerator is a composite of continuous functions, and then the entire function is the quotient of two continuous functions. All right. Similar here, okay? So we have that x minus 2 over x squared minus 2. If we have this as my f of x, we have this as continuous because it's rational. Okay, quotient of two polynomial functions. And we have that g of x equals the absolute value of x is also a continuous function on its domain. And so again, we have the composite of two continuous functions, so this will also be continuous on its domain. Okay? All right. And finally, this one, we have x is a continuous function. So if we have f of x equals x, it's a polynomial which is continuous. We know that for the sine of x, so if I call it, say, g of x equals the sine of x, this is also continuous because the limit at any point on its domain is going to equal the sine of that point. So it's going to be continuous. And then we'll call the denominator here h of x equals x squared plus 2 is a continuous polynomial function. Okay? So that means that the product x times the sine of x is continuous because it's the product of two continuous functions. And then that also means that if we take this continuous function and divide it by another continuous function, this is the quotient of two continuous functions, so this is continuous. And then lastly, if we take the composition of this function with the absolute value function, so we'll call that this. So if we take the composition of this function with that function, we get our function in question, and the composition of two continuous functions is also continuous. Okay, so basically we're just using those properties. We're talking about, you know, if each of the pieces are continuous, then their products are continuous, their quotients are continuous as long as the denominator equals zero, is not equal to 0, and the composite function with two continuous functions is also continuous. All right, so this basically says that if the limit as x approaches c of f of x is equal to b, and g is continuous at the point b, then the limit as x approaches c of g of f of x is simply g of b. Okay, and so that's basically saying that you can actually evaluate the limit of a composite function by taking the limit. So we're taking, in place of f of x, we're taking the limit of f of x and evaluating g at that. Okay. Here's an example. It says find the limit as x approaches 0. Okay. And so basically we have a composite of continuous functions. E to the x is continuous. Tangent is continuous on its entire domain, which includes, so tangent is continuous on its entire domain, which includes x equals 0. Okay. And the square root function is continuous on its domain. And so we basically have the composite of a bunch of continuous functions. So this should be continuous. And we know that if a function is continuous, then its limit should equal the value of the function. And therefore, the limit as x approaches 0 of this function, e to the tan x square root of x plus 1, should be able to be evaluated by just plugging in e to the tangent of 0 times the square root of 0 plus 1. Okay, and tangent of 0 is 0, so this is just e to the 0 times the square root of 1, which is just 1. Okay, so anytime we know that the function is continuous, then we can evaluate its limit by simply evaluating the function.